All right, so this video we'll talk about some examples for lesson 4 where we talked about the OR case of compound events and the special case of disjoint or mutually exclusive events. In these examples you can look at the problem, pause the video, try it out, and then unpause the video and see if you were correct. The first problem says, in a group of 20 children, 3 have red hair, 8 have blonde hair, 4 have black hair, and the rest have brown hair. If a child is chosen at random, what's the probability that the child will have brown hair? All right, so maybe we can just make a little table here. We have red hair, 3 people. 8 people have blonde hair, 8 people. Black hair, looks like we have 4 people have black hair, and the rest have brown hair. But we were told that there was a group of 20 children. So first of all, I think we could use just elimination here and just say the remaining people have brown. We could just add these up. 8 and 3 is 11 plus 4 is 15, and then that leaves 5 left to be brown if we have to have 20. Okay, so what's the probability that a child will have brown hair? Well, if I chose a child at random, then every child is equally likely to be chosen, and that means we can use our equally likely way to find this, that they'll have brown hair. It would be the number of ways to choose the child, number of children, and then this would be the number specifically that have brown hair. Okay, so I think it's just going to be 5 children, right, out of the 20 children, right, which turns out to be 0.25. 0.25. Okay, so another way, or just to kind of tie it in a little bit with the idea of OR, would be, the probability that a child chosen has brown hair, that's going to be 1 minus the probability that they do not have brown hair. They do not have brown hair, right? But if you look at I don't know what's going on with my computer here, it's not very responsive. Okay, so, but the probability that we are not having brown hair is there's different ways that can happen. You could have red hair, or you could have black hair, or you could have blonde hair, right? Okay, so you could have blonde hair. So we would have 1 minus, and what we could do is we could add up the probabilities of having red hair, which is 3 out of 20, with the probability of having blonde hair, right, which is 8 out of 20, 8 out of 20, with the probability of having black hair, which is 4 out of 20. And that turns out to be 1 minus, let's see, 8, 9, 10, 11, 12, 13, 14, 15, 1 minus 15 out of 20, which would be 20 out of 20 minus 15 out of 20, which is another way to get the 5 out of 20. So the reason I included this is just to illustrate that it is true that if I want to know what the probability of having red or blonde or black hair, I could add those cases, and that's because we know that if we're taking combinations of different event probabilities, as long as there's no overlap, as long as a student or a child can't have black hair and blonde hair at the same time, then that means we would simply add the probabilities. But probably what we would do in this case is just focus on the number of brown hair children and then take that out of the 20. Okay, let's do the next problem. Okay, problem 2 says if we draw a single card from a standard deck of 52 cards, we want to know what the probability is that it's a 7 or a face card. Okay, so maybe we could use the OR formula. The probability of being a 7 or a face card, I'm going to use FC for face card. Well, we know the OR formula says that that could be the probability of being a 7, because we're talking about a single event here, plus the probability of a face card. But then we have to subtract off any overlap if there's a chance that something could be a 7 and a face card at the same time, right? But if you think about what a face card means, A face card is a jack, a queen, or a king, something with a human face on it. So it's never possible that a 7 would be a face card. So this probability here is 0. And that means that we could find the probability of 7 or face card by just adding up the probability of a 7 and the probability of a face card. So what is the probability of getting a 7 if I draw a single card from the deck? Well, there are 52 cards in the deck, and 4 of them are 7s, because there's a 4 of clubs, a 4 of spades, a 4 of hearts, and a 4 of diamonds. And then how many face cards are in the deck? Well, there's going to be 4 jacks, there's going to be 4 queens, and there's going to be 4 kings. So 4, 8, 12. There's a total of 12 face cards in the deck. 12 face cards in the deck. So 12 out of 52. And then we would add those. Okay? So that's a total of 16 cards out of the 52 cards are 7s or face cards, which turns out to be a probability of 3077. Okay, so a couple things to notice about that. One thing that I kind of keep in mind is whenever I'm talking about OR cases like this, every time I include a different fraction that represents a probability of an event, like the probability of the card being 7, probability of it being 50, or being a face card, I go back to the original deck. In other words, each one is a fresh start. Right? When we get to this plus sign here, it means that each individual term can fully satisfy the problem. In other words, if we get a 7, then that means the condition is satisfied. If we get a face card, then the event is satisfied. Right? So that's why this is not a 51. Right? It's back to having the original 52 card deck. So if you're wondering why we're not reducing that number, it's because with OR, each individual case starts from the original problem with this original deck. Okay, let's keep going here. It says a community college has 1,000 freshmen, 800 sophomores, 700 juniors, and 500 seniors. If a student is selected at random from this college, what's the probability that the student is a junior or a senior? So the probability of being a junior or a senior, I'll use this notation this time, will be the probability of being a junior plus the probability of being a senior, but we have to subtract off the probability of being a junior and a senior at the same time. So the question is that even possible? Well, I think it's impossible for someone to be a junior and a senior at the same time, so this probability is 0. That means these are what we would call disjoint or mutually exclusive events. In fact, if you were to make a Venn diagram of this situation, you would draw a bubble for the juniors and you'd draw a bubble for the seniors, but you wouldn't have them overlapping because there's no way that a student can be a junior and a senior at the same time. So what would the probabilities be? Well, the junior probability would be 700 out of the, well, we have to figure out how many students there are total. There's 1,000 plus 800 plus 700 plus 500, and that is a total of 3,000 students. So 700 out of 3,000 is the probability of a single student being a junior, and then there's 500 seniors out of the 3,000. So that's a total of 1,200 out of 3,000, which turns out to be equal to 0.4. All right, so these cases where there's no overlap, blonde hair, black hair, juniors, seniors, then we're simply adding probabilities for OR cases. Okay, in problem 4 here, it says in a survey of U.S. households about cell phone ownership, the following data was obtained. There's different numbers of cell phones from 0 up to 4 or more, and there are probabilities. So this is a complete probability model. It says find the probability of, and we'll do these one at a time, having 1 or 2 cell phones. So for part A, right, the probability of 1 or 2 is going to be the probability of having 1 cell phone plus the probability of having 2 cell phones. My computer is really slow today for some reason. probability of one cell phone plus the probability of two cell phones, but I'm not going to subtract off this probability of 1 and 2, right? Because you can't have 1 and 2. You either have 1 or you have 2, so this is 0. So this would just be the probability of 1, which is 0.23, plus the probability of 2, which is 0.35. And that would turn out to be 0.58. Okay, for the second part, it says we want the probability of 2 or more cell phones. So I think what you can see, hopefully, is that every one of these individual events here, 0 cell phones, 1, 2, 3, and 4 or more, they're all mutually exclusive. They're all disjoint. So I could just add them at will without having to subtract everything. So that means the 2 or more case includes the 2. It means we'll add the 0.35 to the 0.28 plus the 0.08. And that turns out to be 0.71. Okay. For part C, it says, what's the probability of having fewer than 2 cell phones? Fewer than 2 would not include the 2, but it would include the 0 and the 1 case. So we'll add the 1 for 0 and the 1 for 1 and get 0.29. Okay. Okay, now for part D, it asks us, are the events having 2 cell phones and having 3 cell phones disjoint? And we said that that would be true. Yes, disjoint or mutually exclusive is the answer here. Why is that true? Because the probability that you have 2 cell phones and 3 cell phones is 0, right? You either have 2 or you have 3, but you don't have both at the same time. Okay. E says, are the events having less than 3 cell phones and having more than 1 cell phone disjoint? So let's look at that. Having less than 3 cell phones would be this case right here, 0, 1, or 2. Having more than 1 cell phone would be everything above 1. There is an overlap here. The case of 2 is included in both. So this one would be no. These are not disjoint, right? Because the probability has an overlap, right? Maybe I should just state it this way. The 2 cell phone case is an overlap. And since they do overlap, it means that, that there is what we call a joint probability. The joint probability would be that 0.35, right? So they're not disjoint because there is a joint probability. All right, let's go ahead and move on to the next problem. So it says a particular model of automobile is manufactured in 3 plants in the U.S. 50% of the cars of this model are manufactured in Detroit, 20% from Spring Hill, 30% from San Antonio, and they provide a tree diagram. It says the events, a car is manufactured in Detroit and a car is manufactured in Spring Hill. Are those events disjoint? So, well, let's see. Is there any way that you can have a car that's manufactured in Detroit and also manufactured in Spring Hill? Presumably, the entire car is manufactured in one spot. So if you go down this path, that's completely different from going down this path. So these two situations, anything that's an end node on a tree diagram, are automatically disjoint. So I would say A, are they disjoint? Yes. Right? If you go down the path to Detroit, you're not going to end up in the same place as Spring Hill. There's no way to be at Detroit and Spring Hill at the same time. Okay, part B says, if one of this model car is selected at random, what's the probability that it was manufactured at the Detroit plant or the Spring Hill plant? So we're finding the probability of Detroit, or, I'll use the or symbol, Spring Hill. Okay, so that's going to be the probability of Detroit and then plus the probability of Spring Hill, and then I'm not even going to bother to write the overlap. You know, there's no subtracting overlap because these are definitely disjoint events. So the probability of disjoint is 0.5, or Detroit is 0.5, the probability of Spring Hill is 0.2, and so this probability would be 0.7. Okay, make sense? Let's see, how many more problems are there? Let's see, 6, 7, 8, so just 3 more to go. Let's take a look at problem 6. Okay, it says a jar contains 10 balls, 4 green balls, 3 red balls, 3 purple balls. A single ball is selected from the jar, then what would the probability be that the ball is red? Okay, so we're talking about a single ball selected. So for A, the probability that it's red, it's just there are 10 balls in the jar and 3 of them are red. So I believe that probability is just 0.3. They're all equally likely. There's 10 possible balls to select from, 3 of them are red. Okay, for B, it's a purple ball. The probability of a purple ball being selected, again, from the 10 balls that you could select from. Looks like 3 of them are purple, so the probability would be 0.3 again that we would get a purple ball. And for the second one, it's the probability that it's red or purple. Right, so that's going to be the probability of red plus the probability of purple, and then minus the probability of red and purple at the same time. But a ball can't be red and purple at the same time. If it's red, it's not purple, so that's 0. So this would just be 0.3 plus 0.3, which would be 0.6. Okay? All right, let's look at this one. It says 2 events, C and D, occur with the following probabilities. And I think these were supposed to be C's and D's. Let's change those. Okay, so the probability of C is 0.3, and the probability of D is 0.6, and the probability of C or D is 0.7. Are the events mutually exclusive? Okay, so mutually exclusive would mean that the probability of C and D is something other than 0, or sorry, is equal to 0. So actually, let's make a little diagram of the situation here. Right? We could have C and D would be what we would call mutually exclusive or disjoint. Right? That means there's no overlap at all. And if that's true, then that means the probability of C and D would have to be equal to 0. Right? Because there's no overlap. There's no way that C and D occur together. Right? If they do overlap, C and D, then that means they're not mutually exclusive. And that means the probability of C and D is something other than 0. So for me to answer this question, I'm going to have to figure out what is the probability of C and D. So how can I do that? Well, I'm given what the OR probability is, and there is an OR formula, right? So could we do this with a Venn diagram? I don't think we can do it with the Venn diagram, because if we try to fill out a Venn diagram, I have to know the inside part first, and that's actually what I'm trying to find. But I do know that the OR formula says this: the probability of C or D is equal to the probability of C plus the probability of D minus the probability of C and D occurring together. So what I could do is I could fill in everything I know and solve for what's left. So they told me that the probability of C or D was 0.7. That would go here. Probability of C is 0.3 would go there. Probability of D is 0.6 would go there. And I'm trying to figure out the probability of C and D. So that's the unknown. So if I just solve this algebraically, 0.7 equals 0.9 minus C and D, we can see that the probability of C and D actually can't be 0, right? The probability of C and D would have to be 0.2, because it'd have to be 0.9 minus 0.2 to get 0.7. So that means there is an overlap. And that means that since this is not equal to 0, that means that these are not mutually exclusive. Man, the board is really slow today. Sorry. Okay. And then it said to find probability of C or D. Well, That doesn't make sense because they gave that to us, right? That would just be 0.7. I think maybe that problem should have said to find the probability of C and D. Let's change it to that. Find the probability of C and D. Well, in the course of finding the answer to the first one, we found that the probability of C and D was 0.2. There is a 20% chance of an overlap. Okay, one last problem here to wrap this up. It says, two events E and F occur with the following probabilities. And again, there's a typo, it looks like. This should be E and F. Okay, E or F. All right, so they give us E's probability, F's probability, and the OR probability, and they ask us if the events are mutually exclusive. Isn't that the same problem we just solved? Yep. Okay, so that won't give us anything further. We'll skip that one. I think we got the idea. The thing I wanted to include here was an example that you had to work out algebraically with the OR formula. This was the key point, that you can use this formula and substitute in anything. As long as there's only one unknown, then you can solve for that, whether you're solving for the or the and, or an individual probability like C or D. Okay, so that'll wrap up the examples we have for Lesson 4.